All right, here we're going to have a look at what effect taking the absolute value of an entire function has on the graph of that function, and then also looking at what taking the absolute value of x does to a function. All right, and we're going to use the graph of y equals 2x plus 1 to illustrate this, and we've selected a domain from -3 to +4. So let's start off by sketching y equals 2x plus 1, and I'm going to specifically find the x and y intercepts of this function, because those are the critical points that I'm going to use when I'm working with my absolute value functions. So my y-intercept occurs when x equals 0, so I get y equals 1. My point there is 0 and 1, and my x-intercept occurs when y equals 0, so x will be -1/2, and that would give me enough information to sketch my graph. However, I have this limited domain, so I need to know what the endpoints of my domain are as well. So let's have a quick look. When x is equal to -3, I'm going to have y is 2 times -3 plus 1, and that's going to be -5. So I've got a point at -3, -5, and when x is equal to 4, y will be 2 4s plus 1, which is 9. Okay, so I have got my endpoints of my domain at 4 and 9, and these points were, okay, so 4 was not included, so I'm going to have a circle, an uncolored circle there, and at -3, -5, that will be a colored in circle, and I've got my x-intercept at -1/2, and my y-intercept at 1, and I'm going to join those points. Okay, so this is my graph, y equals 2x plus 1. Now, let's have a look at what happens when I use the absolute value. So here we're going to have the absolute value of y equals 2x plus 1. Just before we do that, they wanted the range of each function. So our range for this first function is going from -5 to +9 excluded. Okay, let's have a look at y equals the absolute value of 2x plus 1. Now, what that means is that it is going to reflect my graph about the x-axis from the x-intercept. So what that tells me is that everywhere from my x-intercept, maybe I'll just draw a little line here, to the left of my x-intercept is going to be reflected in my x-axis. So that means at this point, -3, -5, all that means is that moves up to -3, +5. Okay, so all I'm doing is reflecting any points that are below my x-axis to the left of my x-intercept up to the positive on the y-axis. So I'm going to be saying that y equals 2x plus 1 is negative or less than 0 for x less than -1/2. So therefore, my absolute value graph is reflected in the x-axis for x less than -1/2. Okay, and there is no change for the right-hand side of my x-intercept. So my y equals 2x plus 1 is greater than 0 for x greater than -1/2. So therefore my absolute value function is also just greater than 0. So no change at all. So that means I can use what I had before. On the right hand side I had 4 and 9. Those points don't change. My y-intercept doesn't change. And my x-intercept doesn't change. So -1/2 and 0. However, that point -3, -5 now flips up and it becomes -3, +5. So I'm going to connect that line and that line over there. So this graph here is my y is the absolute value of 2x plus 1. And what we can see is that our range now goes from 0 up to 9. 0 is included and 9 is excluded. All right, now we're going to have a look at a slightly different graph. And that one is the absolute value of x, just x, inside of our function. So we're not reflecting the whole graph, we're just reflecting the values of x. And what that does is it reflects our original function in the y-axis. And it becomes a symmetrical function about the y-axis. What do I mean by that? Well, let's have a look at y equals 2 times the absolute value of x plus 1. Okay, so to the right of my y-intercept, my graph doesn't change. Okay, so y is 2 times the absolute value of x plus 1 is the same as y equals 2x plus 1 for x greater than 0. And it is reflected, and I'll show you now why. It's reflected in the y-axis for x less than 0. And it might help to just draw a little table of values and just show you why that happens. So if I've got 0 over there and 1, 2, and 3 over there, if I'm taking my absolute value of x, okay, let's have our -1, -2, and -3. If I'm taking the absolute value of x every time, my y is the 2 times 0 plus 1. So at x equals 0, I get a value of 1. Where x equals 1, well, that's positive. So 2 times the absolute value of 1 is just 1 times 2 is 2 plus 1 is 3. My absolute value of 2 is just 2. Oh, I don't know what I'm doing there. my absolute value of 2 is just 2. So 2 times 2 is 4, plus 1 is 5. My absolute value of 3 is just 3. So 2 times 3 is 6, plus 1 is 7. So on the right-hand side, I'm going to get exactly the same values as I would for y equals 2x plus 1. But have a look at what happens on the left-hand side. When x is equal to negative 1, well, my absolute value of negative 1 is going to just be 1. So that then gives me the same answer as on the positive side. And my absolute value of negative 2 is positive 2. So 2 times 2 is 4 plus 1. And what I get is a graph that is exactly the same on the left-hand side as on the right-hand side. Okay? And luckily I've gone all the way to negative 3 because at x equals negative 3, y is going to be 7, and I'm going to need to have a point at the end of my domain. All right, so what we're going to have is we're still going to have our y-intercept as it was at 0 and 1. And on the right-hand side, I'm going to have exactly the same points as I had before. So 4 and 9 are going to be there and not included. Okay, but now I'm going to reflect this line that I've got over here in my y-axis. But now obviously I'm not going all the way to negative 4, negative 4, positive 9. I'm just going to negative 3 and 7, and that's going to be included. So this function here is y equals 2 times the absolute value of x plus 1, and we need to put our point in there. And let's have a look at our range of this function. So the range of this function begins at the y-intercept, so it's going to be 1, and that goes to 9 exclusive.